This is example number 2 on conservation of mass and continuity. So when you have the integral form, it's the continuity equation. When you have the differential form, it's the conservation of mass, but they both produce the same answers. So that's the purpose of this exercise. So let's consider that you have a flow coming in this direction, and it has 6 inches second. You have flow coming out of this, and this is 6 inches second. You have flow coming in here. This is 6 inches second. You have flow coming out of here. This is 6 inches second. Okay, so this is given in the problem. Then also the problem also says that your density is constant. Okay, and we're going to call this 1, we're going to call this 2, we're going to call this 3, we're going to call this 4. Okay, the next thing you have to do in the problem is you need to put a control volume, and I'm going to place my control volume right inside here like this. Okay, um, the next thing you have to do, you have to put a coordinate system somewhere, and I decided to put it roughly. Just assume this is the middle, uh, kind of the middle of all this. Um, and then that's where I place my coordinate system. And now what you want to do is you want to know that I need to find a couple of things. I need to find what my velocity vectors are, and I need to find what my unit vectors are in my problem. And I need to know what my area is in the problem. Okay, so this is B and S, and this is 1, right? So 1 is going in this direction, in the J direction, in the Y direction. So this will be plus 6J. My N for 1 would be, it has to be normal to the surface, okay? So this will be plus J, okay? So just let me write this down here. Remember, N is the unit normal outwards. Okay, going outwards. Okay, so then your delta S, let's call this delta S1, and the problem says, gives you the value of this. This is 1 inches squared. Okay, this is what happens at 1. So let's go at 2. Okay, this is 2, and note that this is going in the opposite direction of x. Okay, so this is going opposite, so this is minus s6I because it's in the x direction, and your unit normal to this will be like this. So therefore you know that it's going in the opposite direction of x, so this will be minus minus I. Your delta S2, that's this distance right here is the area here. That would be, the problem says that this is equal to 1 inches squared. So just think about the problem that you're looking at the cross-sectional area. Okay, that's what he's telling you. Okay, then you go to location number 3. This is going plus J. Okay, it's going upwards, okay, in the Y direction. And then your unit normal is going in this direction, is opposite of Y. This will be minus J. Okay, and delta S3, the problem says is equal to 4 inches squared. You go to number 4, then you have the unit normal in this direction that you can see positive I, and this is also plus j. This will be I. Sorry, plus I, and delta S4 is not known, and that's exactly what we would like to find. So you start the problem, you put the unit vector, you need to put the control volume first, right? This is control volume, okay? Call it CV. So that's the control volume, and that's what we are trying to look for, okay? No, you put the control volume, but what we are trying to look for is this cross-sectional area. So now we move on and we start our the equation of continuity tells you this is the um, double integral, partial rho respect to time plus the enclosed area over my region, my velocity, unit vector delta S is equal to 0. This is equal to 0 because the rho is constant, so therefore it's incompressible flow. And this is the only term that remains 0. So rho, this is equal to rho V N S is equal to 0. Okay, so just this expression can be written as follows. If you are working in discrete openings, so this is rho I 1 to 4, because in my problem I have 4 openings. So 1, 2, 3, and 4. Okay, so then you have this. You have the velocity vector I. Take the dot product N I. Okay, so you have to take the dot product and multiply by your delta S, your area. All that has to equal to 0. Okay, so to do this, let's go ahead and do one step at a time and see what happens. So let's expand this first. If I expand it, I find this is rho 1, V1 dot N1 delta S1 plus rho 2 V2 dot N2 delta S2 plus rho 3 V3 dot N3 delta S3 plus rho 4 V4 dot N4 delta S4 is equal to 0. Okay, so let's work with one term at a time. So first term gives you V1 dot delta S1, and that term tells you all the densities are the same, so you call it rho, and V1 is equal to 6J plus 6J, N1 is equal to J, 1, sorry, this is J plus J. This is dot product multiplied by, this is 1, this is equal to 1. So this dot product gives you 6. So this gives you 6 times rho. The second one is rho 2, velocity vector 2 dot N2 delta S2, and that gives you all the densities are the same. I'm going to call them rho. Go back to your table. This is minus I dot product. This is minus I. So you can see that it's very important that you get that table right. Okay, and the area is 1. If you don't get that area 1, then you're going to be in big trouble. and this dot product gives you plus 6. So this gives you 6 times rho. Let's go to the last term, last two terms, sorry. So this is rho 3, V3 dot product 3, delta S3. That's going to give you rho, all the densities are the same, and this gives you, this is 6J plus 6J dot product, N is minus J, this gives you minus J, and the area is 4, so this gives you 4, and this dot product gives you minus 6, so this whole thing gives you minus 24 times rho. Let's go to the last one. The velocity 4 and 4, delta S4. Okay, so this will be rho, and V4 will be 6 plus 6J dot I, sorry, 6I plus I, and this I do not know, right? This is what we are looking for. It's not known. So I come here, this dot product gives you 6, so this whole thing gives you 6 rho delta S4. So now we apply we apply this equation, the equation continuity. We add all of these quantities and set them to 0. Okay, so if I do that, I find I get 6 times rho plus 6 times rho minus 24 rho, and I'm getting this 6 rho minus 24 and 6. Okay, and plus 6 rho delta S4 is equal, all of this is equal to 0. So this whole thing is going to equal to, if you do a little bit of mathematics here, you can see that you get here 12 minus 24 plus 6 delta S4. I deleted the entire equation by rho. So if you solve it, you can get delta S4 is equal to 2 inches squared. So this is the total area that we are actually looking for in the problem. This is how you do these problems. Now, there's a second way of doing this, and this is using the conservation of mass. Okay, and how do you do the conservation of mass? If you remember, recall from your lecture notes, the conservation of mass was nothing else than how the mass is changing in control volume is going to equal to what all the mass that's going in minus what the mass is going out. Okay, so in our particular problem, you can see that the mass of the system when my control volume is not changing, my control volume is not changing, and my density is the same, so therefore my mass is the same. Okay, so if this is constant, okay, and my control volume is going to remain constant, then what's going to happen is that you can say that this is the mass of the control volume will also remain constant. So therefore, this term, mass of the control volume with respect to time, will give you 0. Okay, so the problem basically says this is the same thing as saying that this is steady. Okay, this is steady. Okay, so if that's the case, then basically what we are saying is what is going in, all the mass that's going in, all the mass that's going in is going to equal to all the mass that's actually going out. Okay, so, and if you remember from the class notes, your total mass flow will be your density times your velocity times your speed times the area. Okay, so let's see how this works for this particular problem. So we have our control volume again. So we have our control volume again, and what we want to do is just remember from our problem, in our problem, we have to identify what goes out. So you can see that the flow here is going out, the flow here is going out, here the flow was going in, here the flow was going out. This was 1, we call this 2, we call this 3, and we call this 4. Okay, and in this control volume, this is what goes out, this goes in, this goes out. So the summation of everything that goes out is as follows. It says that rho 1 v1 delta s1 plus rho 2 v2 delta s2 plus rho 4 v4 delta s4, and then you have summation of all the mass that goes in. It's going to be rho 3, speed 3, and delta 3. Okay, so this is what you have in the problem. And now let's go ahead and apply our the conservation of mass. The conservation of mass says that everything that's going in, right, your summation of in, has to equal to everything on the summation of that's going out. Okay, in our particular problem, you had 3 segments that went out. You have 1 segment that actually went in. Okay, so in our problem, then we go ahead and put everything. So you can see here everything that went out, everything that went in. So what's going in is rho 3, v3, delta s3. That's going to equal to rho 1 v1 delta s1 plus rho 2 v2 delta s2 plus rho 3 v3 delta s, this is 4 4 4. Now replace all the values. For this, all the rows are the same, density is the same. So you go here, V3, this is 6. You only take the value, it's just the magnitude. And then S3, S3 was equal to 4. So this is equal to 4. This is equal to this, all the densities are the same, call it rho. V1, V1 was 6, just take the magnitude. This is equal to 6. Delta S1, delta S1 was 1, so this is 1 plus rho, all the rows are the same in the problem. V2, V2 is minus 6. This is the magnitude. All we care is the magnitude, not the sign. So this is 6. It's not minus. It says 6. And then this will be 1. Delta S is 1. And you're wondering why did I take the minus sign? No, because I only took in consideration everything that goes in is equal to everything that goes out. And that only includes the signs. Okay, so we can leave it like that. And then the other part of the problem is plus all the density is the same. The last 4 is actually 6, so the magnitude is 6. The magnitude is 6. And your S4 is what I'm looking for. This is what I'm looking for, delta S4. So now you can cancel all this, all these. You can cancel these. And you find that your answer is 4 is equal to 1 plus 1 plus delta S4, and delta S4 is equal to 2 inches squared. That was the same answer that we got when we did the continuity equation. So this is how you really use these equations. They're kind of straightforward. You just have to be disciplined into doing this table at the beginning of the problem, and then you will not have absolutely no problems.